How's it going, everyone? Welcome to the third drill of the spring semester. Today we're going to talk about how we can code different things for multi-group predictors, where last week we just talked about dichotomous groups. So we're just going to expand on that a little bit today. I've already run the tidyverse library, and we don't need LM support, sorry. Didn't mean to have that on there. I'll talk about LM support at the end of today's lesson, but I decided against including it in today's lesson. So I wanted to make it clear that this drill, more so than the other drills, really has two distinct components, which is the conceptual side, the actual different coding schemes, and the operational side, which is, all right, now that we've decided on the coding scheme, how do we implement that coding scheme in R? So if you get stuck or confused or you're unsure about some part of this drill, it'll be really helpful to Bill or me if you reach out to me, if you're able to really specify whether it's the conceptual side or the operational side. If the question is, well, why do I interpret this way? That's a conceptual question. But if it's, well, if I want to code, these contrasts or whatever, that's a strictly our question. We're going to see multiple ways to do the same things for each of three different contrast coding schemes. We'll see at least two different ways of putting those contrasts into R. Some people like one way better, some people like the other, tomato, tomato. You only need to know one way. I'll talk about the way that I prefer and things like that. But if you feel like I'm repeating a lot of the same information, then good, because I am. It's just a different way of doing the same thing. So don't feel overwhelmed and like you have to learn all of these different things. You just need to figure out which one clicks with you, and then that's the one that you can use. Like I said, there are other approaches that use other libraries like LM support or certain functions. There may be a library that has one specific function that's good to use in this particular case, but I don't want to flood all of you with, hey, let's have to learn 20 different libraries and a bunch of different specialized functions, and trying to stick with just tidyverse and base R. So the data that we're going to look at today is fake data, and all it is, as you see, we have 20 observations. We have 5 each in groups labeled always, frequent, infrequent, and never, and some other variable called errors, which ranges from 9-ish up to 20-ish, somewhere in there. It doesn't really matter what the data are. We'll just pretend that there is some research design behind this, but I don't think it really matters since we're not too worried about interpreting things today. So what I'm doing today, just for the sake of example, but this is not something that you would necessarily normally do in your data, is I'm going to create multiple copies of this condition variable, and it'll make sense why as we go along. But I'm going to start, we're going to basically, like I said, we're going to do 3 different coding schemes today. We're going to do dummy coding, which is a pretty standardized name. We're going to do what I call, a contrast codes. In this case, it will be planned orthogonal contrasts. And then also we'll look at what's called Helmert coding at the end. So that con.d, con.c, and con.h will end up being the dummy coded condition, the contrast coded condition, and Helmert coded condition. But we're going to start just by using that as factor default condition that we talked about last week, which, as we know, as I mentioned, that means that it will automatically dummy code things. So I'm going to start by running this line, and then we'll explain what it does, because what I'm wanting to do is, I take that back, I'll just go ahead and show you. So the what we're all familiar with, or what you might expect to see, is something that looks kind of like this. If we just take this line out, I know this add row is a new function that you haven't seen. And so this would be something that you've seen before, where we have the data frame, we group it by condition and then summarize the mean, because we just want the conditional means. Well, this add row is a little trick to be able to also get your overall mean in this conditions means without having to run a second function to ungroup and then just get the overall mean without splitting it into its condition groups. So what this tells it to do is to add a row. In fact, I'm going to throw in a view here just so that we can see what happens when we run this part right here. Is it adds a row where it assigns the word overall to the condition, and to errors it assigns the mean of our errors variable in our data frame. So you can see down to the bottom, anything when you use add row, anything that you don't specify just gets filled with NA, but that doesn't matter. All that matters is we now have one additional condition. We now have 5 conditions: always, frequent, infrequent, never, and overall. And the value for errors overall was just the overall mean of those errors. So now when we take that and we group it by condition, like I said, we have 5 groups instead of 4, even though we only had those 4 conditions. And so then when we summarize with errors, it gives us those condition codes plus that overall mean. So I'm going to store that as an object called conMeans. Here you can just ignore this. This is just saying that because after we grouped it and then did something, I didn't ungroup it on the back end. And so this is just saying like, hey, that summarize that this ungrouped the output once you stored it as this object, but it doesn't matter. So if you see that, that's normal. Point is, I just wanted to be able to save a thing called conMeans, condition means, where we see that the always condition averaged 12 errors, frequent was 11 errors, infrequent 16 errors, and never was 16.6 errors. And overall, if we look across all 20 observations, there was on average 13.9 errors. And then if we just look at the mean of that, we can see that indeed that overall does work. So again, this add row is just a little trick of being able to get a grand mean into a grouped mean table, just to kind of have it in one place if you're interested, which I often am. And so that's just a little trick I like. So before we go on today, we need to talk about case when. So we've seen if-else statements before, and we've even seen some nested if-else statements. So say you have, it's not just 2 things, where it's if-else, if x equals 1, then name it 1, else name it 2. Well, what if there are 3 things? Then you have to do nested if-else statements. So you say if-else x equals 1, then return 1, else if-else x equals 2, then return 2, else 3. So you can see that if we had, say 7 different things, we would need 6 nested if-else statements, and then on the back end, it would be something like this, where we just have a ton of parentheses and whatnot. Excuse me. There's a better way of doing this though, and that is case when. So in case when, you just enter in a series of logical tests, whatever that. So like x equals 1, then the tilde, and then the value if that's true. So you would say, 1. And here would be x equals 2, tilde, and then 2. And x equals 3, tilde, 3, and so on. And you can have as many as you want. Now, case when evaluates these things in their entered order. So let's just say that you enter in, because it doesn't have to all be one thing. Say you have your data frame, and say that, case when condition equals always, that the value is, always. And then you say if errors equals 12, then make this the word 12. Well, because always came first in this, all of these that are labeled always will get assigned that word always, and then once it moves on to the next thing, it kind of ignores that. It will evaluate them in the order. So if things are if there are conflicts, then it will evaluate and label in the order. I added this last line here where it says true tilde and then catch-all value. This I wanted to point out because this is something that is, or at least can be, important to know, especially as far as data integrity, because what happens is as K-SWN runs through your values, if you leave something out, R doesn't know what to do with that. But long story short is, if there is something that doesn't match any of the conditions in the K-SWN that gets put into the K-SWN, it gets labeled as true, just on the back end. And so what that does is, if there is something that's true that doesn't have a specific label, it will just make it NA. So in other words, if we have, K-SWN condition equals always, make it 0, condition equals frequent, make it 1, condition equals infrequent, make it 0, and condition equals never, make it 0. So now it will code each of those 4 groups either as zeros or ones as dependent. But if there happened to be somebody in there whose condition was labeled never ever, so it's not one of these specific 4, there's actually 5 labels, since we didn't tell R what to label never ever, it's going to make that particular one an NA. But if you instead wrote the same thing but added this true tilde -999, now that catch-all, it's going to catch anything that isn't explicitly coded for here. It's going to label it as -999 instead of just making it NA. So it's not going to coerce NAs into your data. And you can make this label whatever you want. I use -999 because then if you happen to not check after the fact and then you put this into a regression and you're expecting all zeros and ones, but then all of a sudden you have these really strange numbers, well, it's probably because you have, one thing that's labeled -999 and everything else is zeros and ones. So it makes it easier to kind of catch. This is one of those things. I use this for data integrity and to make sure that there's not some sort of typo or, whatever the case may be that makes it to where I'm missing labels that I shouldn't be. I use it as kind of a fail-safe on myself. The data that we're using today is it's fake data, and it's clean, so we don't have to worry about doing this. There are no missing values or misspellings or anything. But I did want to explain what this line is as far as K-SWN. Back when I taught multivariate in the spring, this was something that we had to learn, so I wanted to pass that along. So first, we're going to look at dummy coding. And when we're dummy coding, we're going to dummy code it such that always is the reference group, which means always will be labeled as 0, and each of the other 3 labels will be labeled as 1 across 3 different variables. So because there's always one less contrast code than there are levels, we have 4 levels, therefore we're always going to have 3 contrast codes. And again, all we're doing is we're saying when condition is always, it's always going to be 0. For D1, if condition is frequent, we'll label it 1. Everything else is 0. For D2, when condition is infrequent, we'll label it as 1. Everything else will be 0. And for D3, where condition is never, it is labeled as 1 and everything else is labeled as 0. But again, that reference group for dummy coding is always coded as 0. Always is always 0. So we'll run this, and then when we look in our data frame, we see that literally all we did was we created 3 new variables in our data set called D1, D2, and D3. For the always group, D1, 2, and 3 are always zeros. For the frequent group, the D1 is labeled as 1, everything else is 0. Same thing here. D2 for infrequent, D3 for never. So that's all we've done is create 3 new variables in our data set. So now we're going to fit 2 models. First, we're going to regress errors on con D, which was that dummy coded. And if you recall, at the very beginning, we just used as factor to factorize that condition variable, because the condition is still just a character. So this is just the default factorized version of this variable. So if we regress, we're going to regress errors on the dummy condition factor from the DF data frame. And we're going to create a model called dummy1. Then we're going to create a second model called dummy1 also, because it's the same model, as you'll see, even though the way that we're going to do it is, instead of regressing errors on this dummied condition, we're going to regress errors on D1 plus D2 plus D3. So on all three of our manually coded dummy variables. But again, the reason I call this dummy1 also is because when we look at our coefficients, we see that these are the exact same things. Our intercepts are the same, and each of our slopes, -1, 4, and 4.6, are all the same. So, we're more used to seeing it in this format, so I'll just show it to you this way, just so that you can see that whenever I use that coef, all I'm doing, I'm pulling these estimates, because I don't care necessarily about our inferential stuff over here. Right now I'm just trying to drive home the point of the estimates themselves. But as you can see, these tables are the same. Everything is identical except for this one is called con D frequent, con D infrequent, con D never, and this one is just labeled D1, D2, D3 because that's what we put in. Now, so since we're dummy coded, let's look back at our contrasts and at our condition means, and look at all this together and look at where all this information comes from. What is our intercept here? Bearing in mind that this model is errors regressed on D1 plus D2 plus D3. So our intercept is the mean where all the other predictors are 0. So let's think, where is D1, D2, and D3? Where does that, all three of those equal 0? Well, the answer is those three only equal 0 in the always condition. If you're in frequent, infrequent, or never, at least one of those variables equals 1. So that's why the intercept is the mean of the always condition. And sure enough, if we look, the always condition, the mean is 12, and that's exactly what we have for our intercept. So then the slope for D1, exactly as it's been before. How do you interpret a slope? Well, it is a 1 unit increase in this predictor is associated with an X unit increase or decrease from the intercept. So let's look back at our data. So a 1 unit increase in D1 means instead of it being 0, it's a 1. Well, there's only one group where that is a 1, and that's the frequent group. So in other words, the slope of D1 is the difference between the intercept, which is the mean of always, and the mean of the frequent group. When we look at our conditional means, we see that the frequent group is 11, the always group is 12, and our slope is that -1, because a 1 unit increase in D1 from always to infrequent is associated with 1 point drop in errors on average. D2, again, it's simply a 1 unit increase in D2 with everything else being 0. A 1 unit increase in D2 is associated with a 4 point increase from the intercept, which again, look at the data. Where does D2 increase by 1 unit? It is for the infrequent group. Look at our means. The infrequent group is 4 points higher than the always group, which is where that slope comes from. And then again, D3, a 1 unit increase in D3, which means the never group, is 4.6 points higher than the intercept, which is that always group. And we can see that here, 12 versus 16.6. So when we're dummy coding things, that's what we're looking at. The reason that this is what it means to be the reference group, the reason that is the intercept, is because this is the only level where everything is 0. And the intercept is the predicted outcome when all the other predictors equal 0. And then each one of these lines, each one of the 3 contrast codes will be with a 1 unit increase in some variable, and whatever your predictor is associated with a blank unit increase or decrease. So again, that's all we're doing is we're comparing. This will be, the estimate is the average of the always condition. The frequent condition is 1 point lower, the infrequent condition is 4 points higher, and the never condition is 4.6 points higher. If you are interested in the significance here, it is not a significant difference between always and frequent, but it is significant differences between always and infrequent and always and never. That may not be the most meaningful analysis, though. That, like, if this was the extent to which people use cocaine, then it whatever the errors is, it might not be surprising that there's a significant difference between people who always use cocaine and people who never use cocaine. So maybe just comparing, these 3 levels to always isn't the most helpful thing. That there are better, more meaningful, more interesting comparisons that you would like to make. But before we get into the next coding thing, I have a note here just to remind you that in this case, condition just happened to be the same as the case when dummy codes that we created, because it happens to be that the condition was labeled always, frequent, infrequent, never, which is already in alphabetical order, which I talked about last week. Alphabetical order is the default ordering method. And so just to prove my point, all I'm doing here is I'm changing always to be labeled as daily, frequent to twice per day, infrequent to once per day, and leaving never as never. And I'm going to create this df2 over here. And then I'm going to do the same thing as before. I'm going to use as factor just to do the default factor. And then when we look at the levels, it's now daily, never, once per day, twice per day. So it's like the highest level, the lowest level, the second lowest level, and the second highest level. It's out of order. And when we run that model using that variable instead of the original dummy one, you can see it gives us the same information, but in a different order. And so, because again, it put it in alphabetical order and then set the first level as the reference level. So you should always, 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 never not double check your contrast anytime you're using factors in a model. Like, you should have this contrasts command and whatever your factor is alongside your summary, and run them so that you can double check and look across your contrast, whether it's dummy coded or contrast coded or whatever, and you can look and see exactly what that is. So now we're going to look at orthogonal contrast. So let's say that instead what we want to do is we want to compare with C1, we'll compare never versus all the others. And so that's like looking at, like, does whatever this thing is, maybe cocaine wasn't the best example, but, we'll stick with that because now we're in it. So does using cocaine at all, ever, versus never, is there a difference there? And then you might say, well, among the people who do use cocaine, where it's either always, frequent, or infrequent, is there a difference between people who always use it versus frequently or infrequently? But, like, we're going to leave out the people, like those wholesome people who have never done it before. We'll leave them out completely. And then we want to see, is there a difference between people who, like, always use it versus frequently and infrequently use it? And then finally, like, let's just compare, like, okay, let's ignore the people who never use it, and let's ignore the people who use it all the time. Like, let's look at the bulk of people there in the middle who, like, frequently to infrequently use it, but, like, not never and not people who use it all the time. So let's just compare those two groups. So those are the 3 contrasts that we're going to do. And so this is what one way of looking at your contrast. And so, you can see here that in C1, never is coded as 3/4, and the other 3 are each coded as -1/4. So you can see how that C1 sums up to 0. C2 also sums up to 0. We're going to compare -2/3 for always against 1/3 each for frequent and infrequent. So it kind of groups these two together. and compares it against this 1. Then finally, in the last one, again, we just have these 2. We have these zeros, so we're ignoring never, we're ignoring always, and then frequent and infrequent are coded as 1/2 and negative 1/2. So again, they sum to 0, and so we could do the same thing that we did before, where we just copy and paste the stuff from above and label it C1, C2, C3, and we create our values just as we've specified here. So frequent, always, infrequent are negative 0.25, never is 0.75. Then here we have negative 2/3, 1/3, 1/3, and 0, 0, 1/2, negative 1/2, 0. So we can run this, and now once again, all we've done is we've taken and we have put in 3 new variables into our data set, C1, C2, and C3, that are coded exactly how we just specified here. Or we can create a matrix and just store it to the factored variable and override that default dummy coding. This is the way that I prefer, and there's a few different ways that you can do this, but this seemed to be the most simple and straightforward way to do it, which is I just create a list of, or not a list in the R proper sense. I write out my 3 contrasts. So the first contrast, C1, I just wrote that I want it to be from the levels lowest to highest. I want it to be coded negative a quarter, negative a quarter, negative a quarter, 3/4. Then for C2, negative 2/3, 1/3, 1/3, 0. So run that one. And then C3, 0, 1/2, negative 1/2, 0. And so then if I plug all those, the reason I do this is because it's one of the easiest ways to kind of keep things separate. And then if you just combine all of those and put it into matrix and tell it that in call, or the number of columns is 3, it can work that out. And so when you run that, it will give you this matrix that looks a lot like this one. And so if we then store that, I'm going to store that as a thing called POC, which is planned orthogonal contrasts. And so if we look at our contrast now for the con.c, I just wanted to remind you that right now it's dummy coded with that first level as the reference group, because we haven't done anything besides as factor the original variable. So now we're gonna override that. The way that we override that is simply we're going to have the contrast, but then we're going to assign our planned orthogonal contrast, POC, this matrix right here, assign that to the contrasts. And now when we look at our contrast, we have that contrast instead of this dummy coding. So now con.c, instead of being dummy coded, it actually has this stored as its contrasts. So now when we put this into a model, instead of using dummy coding, it will use these contrasts. And we can see that here, if we do cont1, and then we look at our coefficients and we look at our table, we can see that, so now our intercept, because this is an orthogonal contrast, which means, among other things, that everything sums to 0, that means that our overall mean is going to be that intercept, or rather the mean of group means. Once again, I just want to point out that that mean of group means and the grand mean are only the exact same if you have a balanced design. In this particular case, we have 5 people in each condition, so the mean of those 4 conditions will be the same as just taking the mean of the overall variable. However, on the homework, for instance, where in one condition there was 44 people and one condition had 42 people, if you take the mean of those 2 groups, it's not going to perfectly line up with just the mean of the DV without the groups. Again, there's a video explaining why on the YouTube channel if you want to check that out. I'm not going to spend time getting into it right now. But point is that if we have our intercept is our overall mean, and we can see that right here. So then con C1, what is C1? C1 compares the never group to the average of the other 3 groups combined. So here I'm just taking my data frame, I'm going to mutate and create a thing called grouping var, and I'm going to use an if else that if it's labeled never, then to label it never. Otherwise, label it as others. And so that's all we've done is now everything is labeled others except for the never group. And now I want to group it by that grouping variable and summarize to get our means. And we can see that the mean of the never group is 16.6, which we already knew. And then if you average 12, 16, and 11 together, you get 13. Well, that difference of 13 and 16.6 is 3.6. So this contrast is comparing these three averages together versus this one, and the difference is 3.6 errors on average. C2, we want to ignore, we're going to take out the never group. We are going to ignore people who have never done cocaine. And we're going to compare the always versus the infrequent and frequent. So we need to lump these two groups together and get their average, and then compare that to the always group. So first, we'll take our data frame. We're going to filter out the never people, take those people out completely. And then again, we're going to group by. If it's always, we'll label it always. And if not, we'll label it frequent and infrequent. Group by that variable and summarize. And we see that the always group, the mean is 12. The frequent and infrequent group, the mean is 13.5. So these are 1.5 points difference between the average of these two groups and this group. And that's exactly what our slope is for that second contrast. And then finally, the third one, we ignore the never, we ignore the always, and we just compare frequent versus infrequent. And we can see, looking at our means, frequent versus infrequent, 11 and 16, the difference there is 5 points, which is where this slope comes from. In terms of verifying orthogonality, there's two ways that you can do it. One is that the sum of all the products of each of the contrasts needs to be 0. So in other words, if we come back to this chart right here, and if we do this negative 1/4 plus, or excuse me, negative 1/4 times negative 2/3 plus negative 1/4 times negative 1/3 plus negative 1/4 times negative 1/3 plus 3/4 times 0. And then we do negative 1/4 times 0, this times this, this times this, this times this, sum all those up. And this times this, this times this, this times this, and this times this, and sum that all up. That's what we mean by the sum of the products, and that's what we're doing here. When we say sum C1 times C2, C1 times C2 will take each of those, make each of those series of multiplications. So here, if we have negative 1/4 times 3/4 is this. Negative 1/4 times 1/3 is this. Same thing, and then 3/4 times 0. So that's all we're doing. And then if you sum those up, you get 0. Then we do the same one for C1 times C3, we get 0. Same thing for C2 times C3, we get 0. The other way that you can do this is you can check the correlations of your contrasts. And the correlations should be 0. That's what orthogonal means. It means that it is not correlated. They are not related to one another. So if we just take the correlation of C1 through C3 from our data frame, we see that the correlations are 0. The diagonals, of course, are 1 because that's C1 and C1, C2 and C2, etc. Anyway, so the sum of the products are 0 for each pair within the contrast, or the correlations of the contrasts are 0. So here I have a try it yourself thing where I encourage you just to run these two lines, look at this contrast, and try to explain to yourself what are the comparisons being made here with these contrasts, and then ask yourself if this is an orthogonal contrast. And down at the very bottom of the script, if you scroll way past the bottom, you'll find an answer key. But I would suggest to try your best to interpret this contrast with no other information and determine whether or not it's orthogonal before looking at that answer. So the last thing that we're going to look at today is Helmert coding. So we've already seen the two ways of entering contrast, either manually specifying contrast variables, or the dummy variables like D1 through D3 or C1 through C3, or manually creating that matrix and storing it as the contrast like we've done here and above. So I'm gonna briefly, very briefly touch on a few of R's built-in contrast functions. So if I just have this line to pull it up, where we can see that they have these different cont R dot blank and the blank Helmert poly sum treatment SAS. These are all different types of contrast that are built into R by default. The treatment is what R calls dummy coding, and so when you put in the function some number, that number is the number of levels in some variable. So if we have 4 levels in our variable and we're wanting to dummy code them, again, the default is the first level will be the reference level. It'll all be coded as 0, and then you have 1 here, 1 here, 1 here. You can enter in the code base equals to change that reference level. So if instead we wanted, the never group to be the reference group instead of the always group, we could change that base 3 or base 4, and now that 4th level is our reference group. Or if we put base 3, then now that 3rd level is our reference group. If you have 5 levels, it will automatically give you your 4 dummy-coded variables. If you have 7 levels, it'll give you 6 dummy-coded things, because remember, you always need 1 fewer than the levels that you have. And by default, that first level with dummy codes, or treatment as this function calls it, is always going to be your reference level. There is this sum contrast, as these call it. Again, don't get wrapped around these labels. It's a coding scheme that you may run into. Some people will call it deviation coding, because what this does, and we'll take a look at it, this compares each group, which is coded 1, to their deviation from the grand mean while ignoring the reference group. So here, in other words, here, because all of these are labeled as -1, it will ignore this group here. And then this first contrast will, the slope would be the difference between, this contrast and the grand mean. This one would be the difference between this group and the grand mean. And this one would be the difference between this group and the grand mean, while ignoring that reference group. I'm not going to, the poly is for polynomial contrast. I'm not going to talk about SAS either. I will talk about Helmert coding, and the authors talk about this a little bit in the chapter. And so the easiest way is just to jump right into, well, let's take a look at what Helmert contrasts look like, and then we can describe what they are, what they do. So as you can see here, what Helmert coding does is it compares successive levels of a factor to all the previous levels of the factor. So right here in this first contrast, it compares always to frequent and ignores infrequent and never. The second contrast compares infrequent to the average of always versus frequent, ignoring never. And the third contrast compares never to the average of always, frequent, and infrequent. So if we now run this, and we look at our summary, again, let me run our contrast, so that, like, this is what I mean when I say whenever you look at your summary, also pull up your contrasts and take a look at those. So here, again, our intercept is that overall mean, and we can also pull up our condition means. So the intercept, again, because this is orthogonal, 13.9. Is our overall mean. So then this first contrast compares always versus frequent. That difference here is only half a point, which we can see. The difference is half a point from the overall. Sorry if you hear my cat back there. Where was I? So that first one compares always versus infrequent, and we see that that's not a significant difference between those two. Then always infrequent versus infrequent. that now there is a significant difference between people who infrequently use it and people who frequently and always use whatever or do whatever. And then finally, that third one is comparing never to the average of all the other three. Sometimes you'll see a thing called reverse Helmert coding, which is basically the opposite. So instead of comparing these two levels and then instead of comparing frequent to always and infrequent to each of these and then never to each of these three, it's kind of just doing it in reverse. So you start by comparing infrequent to never, then frequent to infrequent and never, and then always to the other three. In order to do that, you would have to manually specify that basically just backwards from what you did. And so then over here you can see that that's what we've done. You can check the orthogonality. Again, I label these H1R through H3R because that's just meaning like reverse Helmert coding. And so when we do our correlations there, we can see again that they are uncorrelated, meaning they are orthogonal, because they also sum up to 0. And when we run those, again, everything is interpreted the same. It's just looking at, this would be comparing the H1R is comparing the never to infrequent. H2R is comparing frequent to the average of infrequent and never combined. And then H3R compares always to infrequent, frequent, and never combined. The last thing I'm going to say here before we wrap up is that there are a couple functions from the LM support library that I didn't get into in this year in the interest, like I said at the beginning, of not flooding you with a bunch of functions that you have to remember. But there is, you might look into one called var contrasts as a third way of being able to handle these contrast coding schemes. With var contrast, for instance, one thing is like you could specify a level as a reference. So even with Helmert coding, you could say, as you're putting it in to make your contrast, you can change that reference level to do the reverse Helmert coding, which this might be, it's the only function I know of off the top of my head that allows for functionally doing reverse Helmert coding and not having a manual thing. It also, there are ways of making the labels easier. So for instance, here where we have, if we look at our summary of what would you call it? So if we look here where it's just labeled con.c1, con.c2, con.c3, it just labels everything 1, 2, and 3. It was already called con.c. So this didn't like label it like C1, C2, C3, despite the fact that that's what I named them. That's because the variable was named con.c, it just added the 1, 2, and 3. However, with the var contrasts thing, whenever you use this, you would basically use it in place of this, that there would be a thing that where you say var contrasts and you fill in whatever. So you have whatever your factor is. Type, you would say POC for planned orthogonal contrast. Reference level, you could put that in if you have a reference level, and then POC list would be where you list in your the actual contrast codes, and then there's this labels, and so you could put your labels. So instead of this being labeled as C1, C2, C3, you could call this, say, well, what did we? Like you could label this in your table here. The output might say, instead of cons.c1, con.c2, con.c3, you could change this label to say never versus all others. And this one could be labeled as always versus freak in freak. And this one could, C3 could be labeled as freak versus in freak, or things like that. So there are a few extra steps, but depending on what your personal preferences, that there are some nice features there to be had. There's also another one called var regressors. And basically what that does is, if you go and the way that we set our contrasts here, instead of doing this case when to get all of those other variables lined up, var regressors is a function that will allow you to then just take this con.c after you set your contrast like this. You could take this variable, run it through var regressors, and what it's going to do is it's going to create these 3 new variables and store them in your data frame, so you can go from the matrix to this sort of having 3 labeled variables in your data frame without doing all the case when stuff. So that's just another function in that LM support library that might be worth looking into if you're feeling like exploring some additional things to get out of the base R world. But anyway, that wraps up today's video. Let me know if you have any questions, or if nothing else, I will see some of you on Tuesday.